So, welcome to E-Pathashala for PG courses. We are looking at a series of lectures on computer networks. So, we have been looking at the transport layer protocol. So, we just saw how a transport layer does the job of multiplexing and demultiplexing, and we talked about two flavors of transport layer protocol, that is UDP and TCP. So, we also looked at the details of the UDP protocol. So, now we will take a look at the details of the TCP protocol, which is a much more complex protocol. So, we will look at the services that are provided by TCP and what the header of TCP looks like and how it handles the connections. Now, the goal of TCP, as we already mentioned, is to provide reliable end-to-end transmission over a best effort network, which is the IP protocol, which can lose packets, reorder packets, delay packets, etc. Okay. So, in spite of whatever the IP protocol would do, the IP layer would do, we want to provide reliable end-to-end connection. So, how does TCP do this? Okay. What are the techniques that are used by TCP for providing reliable transmission? First thing that TCP does is it takes a connection oriented approach. So, this would mean that before sending data, it will ensure that the receiver is present at the other side. So, before data is sent, what TCP will do is it will send a request to the other side, check whether a process is waiting at the other end to receive the data or not. Only if the data is, only if there is a process waiting at the other end, it will send the data. So, this is what we mean by a connection oriented mechanism. So, this way we make sure that a receiver is available. So, packets will not be lost because the receiver is not available. Okay. Second thing is TCP adds some kind of a sequencing and acknowledgement information. That is, it kind of gives some numbers to the data that are being sent, so that you can handle out of order packets, duplicate packets and so on. And similarly, to make sure that packets have reached the other side correctly, it also makes use of acknowledgements. So, the acknowledgements will tell you that packets are reaching the other side correctly. So, you have you can use these numbers, sequence numbers and acknowledgement numbers to take care of out of order and duplicate packets and so on. Third is it also has facility to do flow control. That is, now remember that flow control is a problem that is something that is required whenever we have a fast sender and a slow receiver. So, to handle the slow receiver, TCP also allows the receiver, the slow receiver, to control the rate at which the data is being sent from the sender. So, it also handles flow control. It also takes care of retransmission. That is, if packets are lost or packets are in error, okay, it identifies that the packets are in error by means of a checksum, and if it is in error, it would drop the erroneous packet, but it will ask for a retransmission. That is, the packet will be sent again in order to make sure that you are able to provide the reliable delivery. Okay. Also, in the network, if packets are lost because of something like congestion, that is when you have large number of packets coming into the network from various sources and the routers get overwhelmed with packets coming from all over the place, they may end up dropping packets. So, in those cases, when congestion occurs and if a bottleneck occurs at the network, TCP also tries to reduce the rate at which it is sending data into the network, and that in that manner it also tries to do congestion control. So, by adding all these features, TCP tries to provide reliable transmission. So, we will look at each of these and how it does each of these things in detail. Okay. So, first let us take a look at the TCP segment format. This is the header that you have for TCP. You can see that the header is a lot more than what we saw in the case of UDP. UDP, if you remember, has only a 8 byte header, whereas TCP header, minimum TCP size header would be about 20 bytes, plus there can also be some additional options that can be added. So, let us take a quick look at what we have in the TCP segments header. So, you have the source port number and the destination port number. Now, remember, this is very similar to what we had in the UDP protocol as well. So, this is used for multiplexing and demultiplexing. Now, then you can see that there is something called a sequence number and an acknowledgement number. So, just as I mentioned just a little earlier, we said that TCP uses sequence numbers and acknowledgement numbers in order to keep track of which packets have been sent, which are the what data has been sent, what has been received and so on, right. So, we have these two fields which are added for that purpose. In addition to that, there are a few other fields. So, you have something called a header length field, which tells you what is the length of the header. Now, the length of the header could vary because you have a fixed header plus an option. So, if depending on how much of what kind of options are used over here, the length of this header field could vary. So, you have a header length field which specifies that. There are some reserved bits, and then there are a set of flags. Now, we will look at these flags shortly to understand what exactly is the information conveyed by these flags. Okay. And then you have something called an advertised window, which is used for flow control. We will look at that later. So, similarly, there is something called, again you have a header checksum, just as we have a checksum in the case of UDP, here also you have a header checksum. And then we have again the checksum used here is similar to UDP, that is it uses a ones complement addition. And then there is something called an urgent pointer. So, this is again used in connection along with one of these flags over here, we will look at that a little later. Okay. So, now with all this information that you have here with the sequence number, acknowledgement number, advertised window and so on, plus the port numbers. So, all the features that TCP attempts to provide, okay, it tries to do all that with the help of all this information that is available in the headers. Okay. Exactly how it does, how it uses each of this information is what we will look at in the coming slides and the lectures. Okay. So, port numbers, as we said, this we know for sure what this is used for. This is used for the basic multiplexing and the demultiplexing operation, just as in the case of UDP protocol. Okay. So, next we said that remember we said when we talked about UDP versus TCP earlier. So, we had said that UDP is a message oriented or datagram oriented service, whereas TCP is a byte stream service, that is it treats the data that is being sent as a stream of bytes. Okay. So, if I am sending data from host A to host B, some 80 bytes or whatever are being sent. So, it just looks at it as a series of bytes that are being sent from the sender to the receiver. Okay. So, if you look at this and this byte stream is actually emulated using TCP segments. So, a segment can consist of a variable number of bytes, it is not a fixed number, but it is a variable number of bytes. Now, normally a segment is sent by a host side TCP when the segment is full, that is there is something called a maximum segment size which is used. Okay, that is a segment can be a maximum of a particular size. Now, we will see how that is determined later, but right now assume that there is something called a maximum segment size which is available. So, if you have accumulated that many number of bytes in your buffer, the TCP's buffer, TCP will send that much amount of data. But even if it is not full, but there is some kind of a timeout occurs, then also it may send, then it will send whatever data is available. Or similarly, we also have an option wherein the application can push the data out of TCP, that is application can give a command called push, which will push whatever data is there in TCP's buffer will be sent out. So, depending on that, the number of bytes that you have in a TCP segment could vary. Okay. So, and TCP does not look at the data in terms of the segments, but rather it looks at it in terms of the bytes. Okay. So, which means that the sequence numbers that we talk about, right, which are given to the data that are being sent are actually given for the bytes. So, the sequence numbers actually count the bytes of data. Okay. So, if this is my segment that is being sent, the sequence number for this segment will be the number of the first byte that you have in this segment. So, if I start from here, this was my initial sequence number that I started with, and so many bytes have already been sent, and say this is some 8th byte or whatever. Okay. So, the sequence number would correspond to this 8th byte of data. So, this will be followed by TCP's data. Okay. And of course, you will have TCP header being sent and so on. So, now when this reaches the host B, so it will correspondingly it will check whether it is coming in this particular sequence number order, and it will put it in the correct order. Okay. Now, when an acknowledgement is sent, we talked about sequence numbers and acknowledgement numbers, right. So, when acknowledgement is sent for this data that has been received, you will see that the acknowledgement sequence number will correspond to the next expected byte. That is, if let us say for instance, we have received some 20 bytes over here. I started off at byte number 8 and I have received 20 bytes. So, which means the next byte I am expecting to receive will be 28. So, the acknowledgement sequence number will then be 28. So, this is how the sequence numbers and the acknowledgement numbers are handled. That is, every byte is basically what is counted. So, which is why we say that is a byte stream protocol. Okay. Now, we just mentioned something called an initial sequence number. Okay. So, what is this initial sequence number? So, what actually happens in TCP is that when a connection is established, when you start sending data, you do not normally start with the de facto sequence number of 0. Instead, you start with a randomly generated number, which is called as the initial sequence number. Now, how will the other side know which sequence number I am starting with? So, that also is handled as part of the initial connection establishment. So, when you establish a connection, you will send this initial sequence number that you are expecting to start your transmission with. Okay. Now, let us look at this why should I start with this randomly generated number? Why not just use a value of 0 whenever I start a connection? Okay. Now, the reason this is done is basically to handle a practical issue. Now, one of the problems that we have is that So remember that in any end-to-end connection is identified by means of these 4 parameters, that is source IP address, destination IP address and the source and destination port number. So, you have the IP addresses and the port numbers together, which will uniquely identify a connection. Okay. Now, here what could happen is that eventually these port numbers can get used again, or they will get used again. Okay. So, what is possible is that when a new connection is established, if I always start with the same port number, okay, if a new connection is established while an old packet, okay, from some old connection is still in flight, what could happen is that old packet could get associated with the new connection. So, if that happens, then there would be a confusion between whether it between data which actually belongs to some older connection, but is being now received as part of this new connection. So, to handle this kind of a practical issue, what TCP does is it starts off with a random sequence number. Okay. So, that is basically how it will handle this. Now, how is this random sequence number basically done? It is done by changing this initial sequence number over time. So, what is normally done is that it is set from a 32-bit clock that ticks every 4 microseconds, which means this will wrap only once every 4.55 hours. Now, so that should normally not cause any problem with that we talked about just earlier. Okay. So, that is a previous connection being still there while you have the sequence number coming from this, right. This is not likely to happen when you have this much of a wraparound time. Okay. 4.55 hours is definitely not a small amount of time. Okay. But what this of course means is that the host will have to exchange the initial sequence numbers, which they do whenever they first establish the connection. Okay. So, so as I said, the value of the sequence number field in every segment will define the number of the first data byte that is carried in that segment, and similarly the value of the acknowledgement field in a segment will define the number of the next byte that the receiver expects to receive, and the acknowledgement number is always a cumulative acknowledgement number. Okay. So, we will just take a look at an example to see how sequence numbers and acknowledgements are used. So, let us say we have a TCP connection which is transferring a file of 3000 bytes. Assume that the first byte is numbered 10040, okay, 10,040 is the first byte number. Now, the question is, what are the sequence numbers for each segment if data are sent in 3 segments, with the first 2 segments carrying 500 bytes and the last segment carrying 2000 bytes. See, you can have different segments carrying different number of bytes, right. So, the first 2 we say are carrying 500 bytes and the third segment carries 2000 bytes. What will also be the values in the ACK segments? Okay. So, what do we expect? First byte is numbered at 10,040, right. So, the first segment that is being sent, okay, will have a sequence number of 10,040 because that is where it starts, okay, and it carries 500 bytes. So, the range of sequence numbers that it is supposed to have is 10,040 to 10,539. Okay. So, the second segment will have a sequence number of 10,540 because 500 bytes have already gone in this. So, 10,540 will be the starting sequence number for the second segment, and this will have the range of bytes 10,540 to 11,039, okay, another 500 bytes. So, the third segment will have the starting sequence number as 11,040 and it will have 11,040 to 13,039, which is the next set of 2,000 bytes. And what will be the acknowledgement values? The first segment, assuming that each segment is acknowledged as soon as it is received. Okay. So, segment 1 acknowledgement number will be 10,540 because it has received 10,040 to 10,539. So, having received 10,539, next byte expected is 10,540. So, it will show that the acknowledgement number will be 10,540. Second segment's acknowledgement number similarly will have a value of 11,040 after receiving up to 11,039. Similarly, third segment's acknowledgement will be 13,040 after receiving up to 13,039. Okay. So, you can see this is basically how the sequence numbers and the acknowledgement numbers will be given. Okay. Now, coming to establishing a TCP connection. Okay. So, we said that TCP is a connection oriented approach. So, how does TCP do the job of connection establishment? So, this is does by means of a simple 3-way handshake. Okay. What do we mean by 3-way handshake? This essentially is that the sender A will send some message to B, B in turn will send a message back to A and A again will send another message to B. So, there are 3 messages which are exchanged in order to make sure that the connection is established. Okay. So, let us look at what exactly are these 3 messages that are sent. The first message that is sent is called as a SYN message, it is a synchronized message. Okay. So, host A tells host B that I want to open a connection. Okay. Now, if B is waiting at a particular post number to receive this connection, okay, which we will assume it is, then it will send back an acknowledgement that it has received the SYN, that is willing to accept the connection, plus it also sends a SYN saying that it also would like to talk to A, that it would like to open a connection with A. Okay. So, now A has got an acknowledgement for its request, but it has also got a fresh request from B saying that B wants to establish a connection. So, A in turn will send an acknowledgement for B's SYN. So, you can see that SYN, SYN plus ACK and ACK. So, this is called as the famous three-way handshake of TCP. Okay. And when this SYN is being sent, each host will tell the other host what is the initial sequence number that it is going to use. Okay. So, using this combination you establish a TCP connection. So, let us just run through a quick example for that again. So, if you look at the header of the TCP packet, right. So, A's port number will be there, B's port number will be there, A's initial sequence number will be filled, header field will be set to 20, and in the flags field here, okay, there is one flag here called a SYN flag. Okay, there are a number of other flags, we will look at that later, but there is something called a SYN flag. So, the SYN flag being set indicates that this is a SYN packet. Okay, this is a SYN packet. So, now when the SYN packet is set, that it means that A is telling B that it wants to open a connection. Now, this is the first step. Now, second step we said is B has to send a SYN plus ACK packet. So, what will be there in this particular packet? See here the sender port is B's port number and the receiver port number is A's port number. You can see that the port numbers are flipped. Okay. And here in the sequence number, this will consist of B's initial sequence number and the acknowledgement will consist of whatever was A's initial sequence number plus 1, because it is expecting now to receive the next byte. Okay. Header field is given as 20, and you can see that in this set of flags, both the SYN flag and the acknowledgement flag are set. So, these two flags being set indicate that this is a SYN plus ACK packet. Okay. That is your response back from B. Next, we have A's acknowledgement for the SYN plus ACK. So, what will this have? Now, A's port number will be the sender port number, B's will be the destination port number, okay, and it will send a sequence number. And what is it that you have here? B's ISN plus 1 will be the acknowledgement field, because that has given a new sequence number which you have to acknowledge. And you have the ACK field set here. Okay. You can see that SYN is not set, only the ACK is set. So, this indicates that this is the A's ACK of the SYN plus ACK field. Okay. So, on receiving this, B can start sending data, and once A has sent this, A also can start sending data. So, this is basically the three-way connection establishment process of the of TCP. Okay. Now, the question you can ask here is what will happen if a SYN packet gets lost? After all, we are trying to establish a connection. So, if a SYN packet gets lost, what would happen? Okay. If the SYN packet were to get lost, then what could happen is that, I mean, it could get lost for various reasons. Either the packet is lost somewhere inside the network, or the server could reject the packet because its buffer is full, or for various reasons. So, what will happen in that case? Obviously, you will not get back a SYN plus ACK, right? Your SYN plus ACK packet will not arrive. So, if it does not arrive, then you will not be able to send an ACK. So, how long do you wait for the SYN plus ACK to arrive? So, normally what TCP will do is that it will, on the sender side, it will set a timer and wait for the SYN plus ACK to arrive. If the SYN plus ACK does not arrive until your timer times out, then it will retransmit the SYN plus ACK packet if needed. Okay. So, how do you set this TCP's this timer that you have on the TCP sender side? Because we do not really know how far away the receiver is and how long it will take for the receiver to respond. Okay. So, what TCPs normally do is, most of the TCP implementation they use some default value of some 3 seconds or 6 seconds or whatever. Okay. Right. So, this is something that they do. Now, you can see that many times you will have experience of handling this, or rather experience this loss of SYN when we try to establish a TCP connection. So, for instance, it often happens that a user would click on a hypertext link, okay, and the browser, typically what will happen, the browser will create a socket and does a connect. The connect will trigger the OS to transmit a SYN. So, there is a SYN packet, that is a connection establishment is being done. Now, if the SYN is lost, okay, this 3 to 6 seconds delay, because TCP is waiting for 3 to 6 seconds before it will retransmit it. Okay, it can be too long a delay, and the user may often get impatient, right? As a user, you may get impatient. So, what do we normally do? We may go and click the hyperlink again, okay, or click reload. Okay. So, what this will do is that this will trigger an abort of the original connect, okay, and the browser will basically create a new socket and do a new connect. So, since the previous SYN was just lost, this new SYN would reach in time, and it will force a faster send of the new SYN packet, and this, if it is effective, you will find that the page comes back faster. Okay. So, this is something that you will see happening because of this SYN loss. Okay. So, a quick example again of this three-way handshake, you can see what is happening here. So, I am sending out, first client is sending out a segment with a SYN packet. So, sequence number 1200, okay, no acknowledgement bit set here. Now, on the return B sends back a SYN+ACK packet. So, sequence number is 4800, it is sending a new sequence number, initial sequence number, and acknowledges 1201 for in response to the 1200 that it received. Now, similarly, now this will send back an ACK packet, okay, this is an ACK packet. The sequence number here will be 1201 because now this is the next expected byte, and the acknowledgement packet will be for what it has received on the set. So, 4801. Following this, data transfer can take place. Okay. Now, this is about establishing a connection. So, if you have established a connection, it obviously means that we also have to tear down the connection when the data transfer is over. So, basically what we are saying is that once the connection is established, you will be transferring data, but once you finish your data transfer, you can come and you have to close the connection when you need to, when the process is done with its data transfer. So, this closing the connection is done again with the help of another bit which is there in the flags field, which is called the FIN bit. Okay. So, closing the connection happens in the following manner. So, to close the connection, a sender A, okay, or any of the ends for that matter, can decide that it wants to close the connection. Remember that we are having a full duplex transmission going on. So, anybody could decide to close the connection at any point of time. So, a typical sequence could be something like this. Okay. A decides to close the connection. So, what it will do is, it will now send out what is called as a FIN message. So, in response to the FIN message, B is expected to send an acknowledgement indicating that it has understood that A is closing the connection. Now, B could still be sending some packets to A, okay. So, that could still happen. So, which means A is still receiving packets that are being sent by B. Then, when B is done with its data transfer, B can send a FIN connection. In response to that, A will send an ACK, and that closes the connection. So, you can see that this is not a 3-way handshake as we saw, but this becomes almost like a 4-way handshake. There are 4 explicit messages that are being sent, that are sent for tearing down the connection. You can also have a situation which is slightly different from that. We will take a look at that, but before that let us take a look at this simple example which shows what we saw just now. Okay. So, what is it that we are seeing here? This is the client is sending a FIN segment with a sequence number of 2500. So, in response to that, server sends back an ACK with 2501 and the sequence number is 7000, the data that it is sending, right. Now, then server now decides to close the connection. Now, it sends the next segment with the sequence number of 7001, okay, and it sends a FIN packet. In response to that, this fellow will send back an ACK with the sequence number is 2501 and its acknowledgement as 7002. Okay. So, this is the acknowledgement that is being sent. So, this is how the 4-step connection termination will take place. So, as I said, you can also have slightly different ways in which the connection could be terminated, which is like this. So, A sends a FIN, okay, to B saying that it wants to close the connection. Now, B meanwhile, by the time it receives this FIN from A, B also could have decided that it wants to close the connection, which means B also wants to send a FIN to A. So, what it could do is, it can combine both the FIN and the ACK together and send it as a FIN+ACK packet. Okay. So, you have a FIN, in response to that you are sending a FIN+ACK. So, this acknowledgement acknowledges the FIN that was sent by A, and now you are sending a FIN from B to A. In response to that, A will send its acknowledgement and this will close the connection on both sides. So, this is something that could happen. There is yet another situation also that could occur, which is that both A and B at the same time decide to close the connection. Okay. So, what will happen in that case? A sends a FIN, B also sends a FIN, okay, irrespective of what is happening on the other side. So, what will happen? The fins would actually kind of cross each other, okay. But once A's FIN reaches B, B will send an acknowledgement for that FIN, okay. And similarly, once B's FIN reaches A, A has to send an acknowledgement for that. Only when both these acknowledgements, when the acknowledgements are received by both sides, then the connections are closed on both sides. Okay. So, these are various possibilities that you have. You can also have a situation where these two ACKs could actually cross each other also, okay, that is also a possibility. So, all these different combinations have to be handled by TCP, they are effectively handled by TCP. Okay. Now, coming to the flags that we talked about, okay, we said that there are 6 different flags that are used, of which we already actually looked at 3 flags. We looked at the SYN flag, the FIN flag and the ACK flag. SYN, we said, is used to synchronize the sequence numbers when you start the connection. This is for connection establishment. FIN is used to terminate the connection, finish the connection. The ACK we saw indicates that the value of the acknowledgement field is valid. It is used to send acknowledgement for opening and closing connections, plus it is also whenever the acknowledgement field has a valid value, this ACK bit will be set. Other than this, we have these 3 different flags. One is reset, which indicates that the connection must be reset. Okay, this means that irrespective of whatever is happening, just throw out everything, reset the entire connection. Urgent is a very special flag which is used whenever you are sending some urgent data along with the regular data that is being sent. Okay, it is almost like saying you have an urgent mode where some express data can be sent along with the regular data. Okay. So, in those cases the data will be sent as part of the as the initial part of the data segment, and you will have that an urgent pointer that we saw in the header field which will be set. So, this urgent flag essentially tells us that this urgent pointer field is valid. Okay. This is one other flag. The other flag that we have is a push flag. Now, this push is used whenever the application wants to tell, the sender side application wants to push the data out quickly to the other side, and this push data has to be delivered to the receiver process quickly. Okay. So, we have something called a push flag. So, otherwise normally it would wait for the sequence of exchanges to be complete, right. So, this push is typically used when you want to push the data out, that the application is telling TCP do not wait for data to be accumulated, but just push this data out. Similarly, on the other side, as soon as the push data is received, it has to be delivered to the application immediately. So, that is what is done with the help of these flags. Okay. So, with these flags and these and the basic fields that we have in the header, TCP takes care of all the other features that are available that we have. Okay. So, to summarize what we have looked at today are TCP's features, the format of its header, and the connection setup, the 3-way handshake, and how connection can be teared down. Okay. We also looked at the purpose of the various flags that are used. So, how TCP takes care of flow control, congestion control, retransmission and so on are reserved for a future lecture. Thank you.